It's my pleasure to introduce Ryan Mann, who's an ex-student from UTS, who's currently a postdoc at the University of Bristol. And today he's going to be talking to us about some great work he's been doing over the last year or two on approximation algorithms for quantum partition functions. Over to you, Ryan.
Oh, thanks. I'm going to be talking about how to establish an efficient algorithm for approximating a partition function. And this is joint work with my former colleague, Tyler Helmuth. He was at the University of Bristol, but has now moved to the University of Durham. Same with me. You can find this paper on arXiv or the Journal of Mathematical Physics. Thanks very much for inviting me. And thanks for staying late, as it's acceptable time to be drinking in Australia right now. So let me give an overview of what we like to do. So some subset of the audience would believe that quantum computers can outperform classical computers at a number of tasks. So these tasks can include like combinatorial optimization, machine learning, or quantum chemistry. But you'd want to know when do we get advantage. So our goal is in this talk will be to understand when quantum algorithms provide an advantage and when they don't. And in the case that they don't, or in the case that they do, we'd like to provide formal evidence. We'd like to give some statements saying unless something we don't believe happens, then quantum computers outperform classical computers at a particular task. And in the case they don't, it means that the problem can be solved classically. And what we'd like to do is establish an efficient classical simulation algorithm that solves the same problem. So that's just an overview. So there's one particular approach to this, and this is quantum complexity transitions. So the goal here is we've got some physical parameter beta. So this can be like any physical parameter, but I've just chosen beta, which will become apparent later. And what we'd like to do is identify some critical value of beta, so some constant, depending on somewhat on the system, but not particularly on the system size. And in the parameter regime where beta is less than this beta critical, what we'd like to do is establish an efficient approximation algorithm for some problem that we're interested in. And then when beta is above this critical value, we'd like to provide formal evidence of a hardness of approximation, saying that there essentially is no algorithm that could solve this problem. So this is like similar to the definition of a phase transition. So what we're trying to do is identify complexity transitions with phase transitions in physics. So there's been recent success in doing this in the classical literature. So examples include like this independence polynomial, the matching polynomial, and like the Ising or Potts model. And what we'd like to say is like, can we apply these techniques that have worked quite well in the classical situation to quantum systems? So that's the main goal of this talk. Now just let me give some background definitions. So we'll be interested in two different types of approximation. So the first is an additive error approximation. So if you're given two positive real numbers, x and y, we see that x is an additive epsilon approximation to y if just the distance between them is at most epsilon. And then the second type of approximation, called a relative error approximation, or also called a multiplicative error approximation, would be if we see that x is a relative epsilon approximation to y if the distance between x and y is at most epsilon times y. And this goes relative because the error is relative to y. Or multiplicative because the approximation is preserved under multiplication. So if you want to apply x by some value and y by something, you've still got an epsilon approximation to it. So that works well for real positive numbers. But what about complex numbers? So if we're given a complex number, for a relative error approximation, we require a relative error approximation to the norm and an additive error epsilon approximation to the argument. And this makes sense because if you're given two complex numbers and you multiply them together, then the norm is multiplied together and the arguments add. So we still have this property that the approximation is preserved by multiplication by a complex number now. So that's the first set of definitions. The second set of definitions, we're going to define a quantum spin system. So we're going to model this by a hypergraph. So this is a collection of points and edges between them. And these edges can take up like two or more of these points called vertices. And each vertex, we're going to associate a finite dimensional Hilbert space. So you could just think of on this hypergraph there being a qubit at every vertex, and then the edges are going to denote an interaction which just assigns a self-adjoint operator to that edge. So you could think about this as just being terms in Hamiltonian that you apply to those qubits. So then the Hamiltonian is just a sum over all of the edges in the hypergraph of this self-adjoint operator. So that's the Hamiltonian. And the partition function, depending on some value beta, which is the inverse temperature, it's just the trace of e to the minus beta, and then this like Hamiltonian. So this depends particularly on the hypergraph that you're given. And we're going to allow beta to just be like a complex number. So it can be real, in which case you'd say it's the inverse temperature, or it could be like purely imaginary, in which case it would be time, or it could just be like a combination of both of those things. So we're just going to let beta be any complex number. And we're going to assume the operator norm of each term is at most 1. So the norm associated to the self-adjoint operator on each edge is at most 1. And we can always do this because we can just rescale beta to make sure the operator norms are at most 1. In this talk, we're going to restrict ourselves to graphs. So you can extend this work to hypergraphs, or it also works for multi-graphs. But we're just going to consider 2 local interactions which correspond to graphs. So that's you're probably all familiar with this. But let's talk about how hard the problem of approximating this partition function is. This diagram denotes some complexity classes, and roughly speaking, like the more circles or problems in, the easier it is. So right down in sort of like the easiest class, we have P, which is the class of problems that can be solved in polynomial time. Above this, we have BPP, which is essentially P with some randomness. BQP, which is the class of problems we solved in polynomial time by a quantum computer with bounded error, which in particular includes factoring. And obviously, we don't know if factoring is in BPP or P, and this could still be true. And then way up here in this hard class called P to the gap P, which, let me describe what sharp P is first. So we can think of sharp P is like counting the number of solutions to a problem in NP. So if we think, so how I like to think about it is if P is like a Boolean function, a problem in P would be, does this input to the Boolean function output 1? A problem in NP would be, does there exist an input to this Boolean function that outputs 1? And sharp P would be, how many inputs to this function output 1? And gap P is just the closure of sharp P and a subtraction. So if you've got 2 sharp P hard problems, it's just taking 1 minus the other. So it's like how many solutions are there to this problem minus how many solutions are to this problem. So these complexity classes may seem the same, and they are up to if you just allow polynomial time. But the key point is that hardness changes under approximation. So if you can approximate a sharp P hard problem, that doesn't necessarily mean you can approximate the gap P hard problem. So how hard is approximating the partition function? Well, it's all the way up here in this hard class, which is called P to the gap P, or gap P hard. And it's actually even that hard if we just want to reproduce a relative error approximation to it. But similarly, if we were allowed additive error approximation, this would be BQP hard. So it's actually equivalent to solving any decision problem a quantum computer can in polynomial time with bounded error. Okay. So let me state what the main results of our work are. So, well, firstly, I'll define this fully polynomial time approximation scheme called an FP-TAS. So it's a sequence of numbers. So you can think of this n as just denoting the problem size. And an FP-TAS is a deterministic algorithm that for any n and any epsilon produces a relative epsilon approximation to this number in time polynomial in n and 1 over epsilon. So it's just saying there's like a polynomial time algorithm in n and epsilon that gives you a relative error approximation to the problem you're interested in, which in our case is the partition function. So what our main result says is that if we fix delta, which will be the maximum degree of the graph. So for those that don't know, this would be for any given like qubit in your system, what's the most number of terms in the Hamiltonian that act on that term? So if we fix this to be some constant, there's an FP task for approximating this partition function for all graphs, and all interactions of maximum degree at most delta, and all complex numbers beta such that the norm of beta is at most 1 over e to the 4 times its maximum degree. So this gives you it's like a lower bound on where this complexity transition would be, because we give an algorithm for all inverse temperature or all time evolutions that are below some constant which depends only on the maximum degree of the graph. So that's our main result. But let's see what's previously been done. So in this plot on the right, this is the complexity of beta in complex planes. We have like the real axis and the imaginary axis. And sort of areas in like blues and greens are going to be areas where we can efficiently approximate the partition function. Harrow, Meriband, and Solomon-Manafar in 2020 gave an FQP task. So this is the same definition as a FP task, except from polynomial-time algorithms are now quasi-polynomial-time algorithms. So instead of being like n to some constant, it's now like n to the log n. Okay, and their algorithm works whenever beta is smaller than this constant. And then Kuaha, Kato, and Brando improved this to a fully polynomial-time approximation scheme. So they reduced this complexity from quasi-polynomial-time to polynomial-time, but on a slightly smaller regime. And our contribution is that we give an FP task on like a regime that's larger, at least in the case for boundary degree graphs, than both of these results. And while this is only like a modest improvement on what's already known, like our main contribution is like how simple the analysis is. Like I think our paper's only like 6 or 7 pages. So that's for how easy the problems were. But now what do we know about like when the problem is hard? So in independent work, Sly and Son and Galnis, Stefankovic and Vigoda showed that it's NP hard if you allow beta up to these particular values along the real line. So in this case, there's no approximation scheme unless some complexity condition that we don't believe holds, which is like, does RP, like randomized polynomial time, equal NP? And then if you apply techniques from Bremner, Joseph, Shepard, Goldberg and Go, and this paper with Mick, then you can show that the problem is actually sharply hard along the imaginary axis if you allow beta to go above some constant which also scales as like 1 over the maximum degree. So this is giving like an almost tight phase transition, because these constants scale as like 1 over the maximum degree, and this like hardness also scales as 1 over the maximum degree. So now there's like a constant gap between where we know there's an efficient approximation algorithm and where we know that there's no approximation algorithm unless like a p equals sharp p. And then I think this came out by, well, this is Galnis, Goldberg, and Herrera-Poyotis. And this only came out a few weeks ago. And they showed that the problem is sharply hard to approximate on everywhere apart from you see this region. Essentially all of this red area, but I missed this. Yeah. So in particular, it excludes the real line. So it should be hard like anywhere in this red area apart from the real line. So we're almost, what we'd like to do ideally is get rid of this black area and have like a nice transition between blue and red. Okay, so how does our algorithm work? So our algorithm is based on the cluster expansion. So I'll just give you some history of this. So it's introduced by Mayer when he was studying imperfect gases all the way in the 40s. And since he first introduced it, it's been like made more abstract and simplified. And we're particularly interested in this like abstract polymer model formulation by Kotecký-Preiss. And then we're going to combine this with this quantum cluster expansion, which I think was folklore, but it appeared in Uglitsch's thesis in '98. And then we're going to apply the algorithmic framework of Helmuth, Perkins, and Regts from 2019. And combining these ideas, we'll see how to get our algorithm. Okay. So what I'm now going to define is like, well, as the title says, it's very abstract. But what is an abstract polymer model? So it's a triple. So there's three things. The first is just a countable set of objects called polymers. So this can be like a set of anything you want, provided it's countable, just like any kind of mathematical object. And I think that you can apply this in like very like general situations. So we just have some set of objects called polymers, and then we have a weight function which just takes each polymer and gives you a complex number, and this will be called like the weight of each polymer. And finally, we just have a symmetric compatibility relation. So this says like if you're given two polymers, it just says are they compatible or not. And this is always, well, this is symmetric, so that if A is incompatible with B, then B is incompatible with A, and a polymer is always incompatible with itself. And we just say that a set of polymers is admissible if they're all pairwise compatible. So if you're just given a set of polymers and they're all compatible with each other under this compatibility relation, then we say it's an admissible set. We're going to denote by G the collection of all admissible sets in the polymers. And then given this framework, we define a partition function called the abstract polymer model partition function, which is now just a sum over all possible admissible sets of polymers. And then just for each admissible set of polymers, it's just a product of their weight function. And this is called the abstract polymer model partition function and captures like a very wide class of well-known partition functions. So this is very quite abstract. So let me give you an example, which is not to do with quantum computing, but is far simpler. So if we've just given some graph, we're going to let the collection of polymers just be the vertices of the graph. And then we're going to say that just the weight function is just going to always just be some complex number Z. And then we're going to say that two polymers or two vertices are compatible if they don't have an edge between them. So these would just be independent. So in this graph here, these two vertices don't have an edge between them, so they're compatible. These two do, so they're incompatible. And then an admissible set is just a collection of vertices that don't have any edges between them. So this is called an independent set. And then the abstract model partition function, which would be a sum over admissible sets, is now like a sum over independent sets. And then it's just a product of how many terms are of the weight are in that independent set, which is just Z to the power of the size of the independent set. And this thing is just the independence polynomial. So this is well known in statistical physics, combinatorics. And I'll later relate this to quantum setting. So we're given some abstract polymer model. We can define an abstract model partition function. We can define the abstract cluster expansion. So this is a formal power series for the log of the partition function. And this is defined as like a sum over clusters. So let me define what a cluster is. So if we're given a tuple of polymers, so a list of polymers, and they can be repeated in this situation, we construct this thing called the incompatibility graph. So for each polymer, we add a vertex to this new graph. And then if two polymers are incompatible, we add an edge between them. So independence polynomial, the incompatibility graph would just be like the graph itself, or the induced graph by the tuple of polymers. And then we say that this tuple of polymers is a cluster if this graph is connected. So it means that given like a tuple of polymers, you should be able to get from one polymer to any other polymer by just like a sequence of incompatibility relations in that tuple. And then we're going to denote by GC the set of all clusters. So this abstract polymer, abstract cluster expansion is just a formal power series for the log of the partition function. So we sum over all possible sets of clusters, and then we have some combinatorial factor, which is called the Ursel function. So this just depends only on the structure of this independence of this incompatibility graph, and then it's just a product of weights in the tuple of polymers or in the cluster. So so now we have this this abstract cluster expansion, but it's only a formal power series. So to be useful for approximations, we need to show that this object converges. So a very useful theorem from Kotecký-Preiss in '86 just says that if you're given two functions which take a cluster to a positive real number, take a polymer to a positive real number, such that this inequality is satisfied. So what this is saying is that you want to sum over all polymers that are for every polymer you want to, or for any polymer you want to sum over all polymers that are incompatible with that, and then take the absolute value of the weight, and then you want to show that decays exponentially in these functions a and d, and satisfies this inequality. And if that's true, then we guarantee that the cluster expansion converges absolutely. We know the partition function is non-zero, which you sort of need because you're going to take the log of it and you don't want to take the log of 0. And I won't describe what this means, but essentially it gives you a good bound which you can use to show that if you truncate the cluster expansion, you get a good approximation to the log of the partition function. So you get, so for an example of like the radius of convergence, for the independence polynomial, you could say this is like 1 over e delta plus 1, or Scott and Schokl in 2005 showed the radius of convergence is this value. So delta here is again the maximum degree of the graph for the independence polynomial. And this is exactly Cire's region of the Lavash local lemma. So what our algorithm is going to do is we're going to rewrite the problem as an independence polynomial, except from the graph is going to be more complicated. In our case, it's actually going to be an infinite graph, and the weight function is going to be also more complicated. Okay, so now let's construct an abstract polymer model for our partition function we're interested in. So let me just describe what they are, and then I'll try and explain how you get to them. So in our case, a polymer is now a multi-set of edges. So this is just a set of edges and then just a multiplicity function, which says how many of that edge is in the multi-set. And we want this particular multi-set to induce a connected subgraph in the graph. So if you were to sort of draw these edges on over the graph, that what you'd end up with would be connected. And we'll define the size of a multi-set of edges to just be the number of edges in the multi-set, including multiplicity, and just the cardinality of support to be the number of edges in the polymer, not including multiplicity. Then the weight function is some like combinatorial function, which depends on beta. And then this term, which is like a trace over all possible permutations of the product, of the order of products you could take of the interactions in this multi-set. So you may think like, where did this come from? So let me just give you some intuition. So suppose you're starting with like e to the minus beta h, you're going to take the Taylor expansion, and then like the terms in the Taylor expansion are going to be the sum over all possible sequences of terms of the Hamiltonian. And then for a particular sequence, you're going to break it up into regions that act on disjoint qubits and like aren't connected to each other. And then this is an admissible sequence of polymers. And what you need to do is you need to count how many times this occurs, because there's like several different sequences that can give the same admissible set of polymers. So this is like where this this combinatorial factor comes from, and that's roughly how you would obtain like an abstract polymer model for the partition function we're interested in. And I shall say we say that the two polymers, or two of these like multi-sets of edges, are compatible if they're supporting subgraphs of vertex disjoint. So we're really breaking the Hamiltonian up into like local regions, and then we can write the partition function as this abstract polymer model. So it's like a sum over admissible sets of polymers, and then just like a product of the weights of them. So it's quite technical, but the main contribution of this is that we get a cluster expansion for log of the partition function. And once we've done that, all we need to do is obtain additive error approximation to the log, because that corresponds to a relative error approximation partition function, which is what we wanted in the first place. So a useful thing in the quantum cluster expansion is to consider a truncated quantum cluster expansion. So we're now going to define like the size of a cluster should just be the sum of the sizes of the polymers in that cluster, and divide the truncated cluster expansion to be the same as like the regular cluster expansion, apart from we're only going to consider clusters of a certain size up to this particular m. And then we can prove the following lemma, which says that if we fix the maximum degree of the graph, and then let beta be a complex number such that its norm is at most 1 over e to the 4 delta, so this ensures convergence. We have that the cluster expansion for log of our partition function converges absolutely. It's non-zero, and we get this good approximation, which says that the difference between the truncated cluster expansion and the log of the partition function is at most the number of vertices in the graph, and then e to the minus m, and this holds for all m. So let's say the proof. So the proof just uses this Kotecký-Preiss convergence criterion with some facts about boundary degree graphs, which you need to count how many polymers are incompatible with a particular polymer. But the key point in this lemma says that if you take m to be log the number of vertices over epsilon, so you can plug it in here, then this just gives you an epsilon additive approximation. So the key point is that all we need to do to obtain our relative error approximation to the partition function is to obtain we just need to compute this truncated cluster expansion to order logarithmic in the number of vertices over the error that we want. So the rest of the time is going to be devoted to doing this. So for this, Helmuth, Perkins, and Regts showed that such an algorithm exists if we're given 3 lemmas. So firstly, we need to be able to list the clusters. So the first lemma is that the clusters of size m can be listed in time exponential in m, and then just like some polynomial in the number of vertices. We're allowed exponential in m because we're just taking the logarithm of it. So this will give you a polynomial time algorithm for what we're interested in. And the proof is just a slight modification of Helmuth, Perkins, and Regts. So in the classical case, you get like a similar expansion, apart from you don't need to deal with multi-sets of edges. You can just do it with sets of edges. The second lemma is just that the cell function can be computed in time exponential in the number of vertices. And the proof for this is actually you can just rewrite this cell function as the evaluation of a tuplet polynomial at a particular point. So this was shown by Helmuth, Perkins, and Regts, and this paper by Björklund and others showed that you can compute the tuplet polynomial in exponential time, where it was previously thought that wasn't true. The next lemma is that the weight of a polymer can be computed in exponential time. The proof is that this is a matrix value permanent, so we can use inclusion exclusion. So let me just go back to the definition of the weight. So this particular weight is like a sum over all permutations. So this is sort of like a permanent, apart from like these things are now matrices. So for Rice's algorithm for computing the permanent in exponential time also works in this situation. We just have to deal with matrix valued entries. Although if this was the determinant, I don't know a way to do it. Okay, so now given this, the final lemma we need is that the truncated cluster expansion can be computed in time exponential in m, and then polynomial in the number of vertices. And how you do this is first you list all clusters. Then for each cluster, you compute this cell function. And then once you've computed the cell function, you compute the weight of the polymers, and then take a product of those in the cluster. And if you do this to every cluster of size m, then you can compute the truncated cluster expansion. So the proof is just combine the lemmas above. And that gives us our algorithm. So let me give some physical intuition about how this algorithm works, or like why this should work. So the first is analyticity of free energy. So in this case, we're going to consider a sequence of graphs. So you could think of it as being like the square lattice. And we're going to consider it in the infinite volume limit. So we're going to take the limit of this graph sequence of the log of the partition function divided by the number of vertices in that sequence. So this is the free energy in the infinite volume limit. So these are like infinite volume phase transitions. And we know that this function is non-analytic when the partition function is 0. So we're restricting ourselves to like a regime where we know that this free energy is analytic. And the physical phase transitions are exactly the real limit points of the complex zeros of the partition function. So if you consider like along the real line, you just imagine a real beta, at least for like an Ising model where you know the partition function is never going to be 0, where a phase transition occurs, it's just like the limit point of where these zeros approximate or approach the real line. We also have uniqueness of the Gibbs measure. So the Gibbs measure, I guess the key ingredient is you're dividing by the partition function. And again, if this is 0, then you're dividing by 0, and this is non-analytic. And you also have exponential decay of correlations. So how our algorithm is working is saying you only need to consider like local clusters and compute those. And if you combine them in the right way, that'll give you a good approximation. So it's actually saying in this like high temperature regime that the state of a particular spin like is independent of its boundary conditions. It only just depends on like what's locally around it. Our algorithm works in like the high temperature regime because you're saying that like beta has to be small, which means that the temperature has to be high, or just for short time evolution, like if you were to replace beta with like IT, you'd be able to approximate this function for small time evolution. And it also allows you to interpolate in a phase. So like once you're in like an easy phase, you can use this interpolation to get to other easy points in the phase. But as soon as you reach a phase transition, this interpolation method fails, and there's just nothing you can do. Okay, so that's sort of like the end of how our algorithm works. I think like the key point was, well, while you may disagree from hearing it, like how simple it was. But now let's just try and expand this method to like other problems we might be interested in, to like really show how versatile this technique is. So we're now going to apply it to quantum circuits. So this is like much easier than Hamiltonians. You didn't have to deal with like multigraphs or multisets or anything like this. But if we just consider some quantum circuit, which is just a product of say like 2 local unit trees, we're going to do everything in reverse order. So like it'd be like I1 times I2, just for convenience. And then in like the classical literature, they have this trick called the +1 -1 trick, where you just add +1 to something and -1 to something to keep it the same. So we're going to do the plus identity minus identity trick. So we're going to define this U hat as just being U minus I. Then our circuit is just identity plus U hat, and then just like a product over those. But this is just the same as like a sum over all subsets that you get from this and then like a product of the UX's inside that subset. And this is just an abstract polymer model where a polymer is now a connected subcircuit. The weight of a polymer is just a product of this U hats, which are inside this subcircuit. And then we just say that two polymers are compatible if their subcircuits act on different qubits. So if the subcircuits are qubit disjoint. So applying this, you can obtain an efficient approximation algorithm for computing like the all zero amplitudes of this quantum circuit, provided C is bounded degree. So that would mean sort of the same as it would in the Hamiltonian case, where it's saying that the number of gates that act on any single qubit is at most delta. And we also need some conditions. So before we needed the beta was bounded from above. And in this case, we just need the unitary is, each unitary is just close to the identity. So you could also, instead of like having this product over UIs, you could write UIs like e to this like some Hamiltonian that generates the unitary. And then you could just apply the same algorithm as before, only it would be like still quite messy. And you'd have like some similar condition on like how small this like theta would need to be in the Hamiltonian. And that would give you like a similar result. Okay, so that was like one new approach that we've applied it to. Let's now try and do it to the mean values problem. So the theorem by Bravi, Gossett, and Moser gave an FP task for computing this mean value for a constant depth quantum circuit U and a product operator, which is just like a tensor product of other operators when this operator is close to the identity. So this is similar to the quantum circuit. Actually, like the proof works in a similar way before. So we're going to define this operator hat as being like the operator minus identity. Then we use the same trick before. So we can now write this thing as an abstract polymer model where the subset of the polymers are subsets of operators that are like cone connected. So that just means that if you were to consider like a particular operator inside this circuit and then sort of trace through what gates it ends up affecting, that would be its like cone. And we say that like a subset of these is like cone disconnected if these like codes never touch the same qubits. And then like a weight is the same before. It's just well, it's just like this mean value where you just like put the identity and replace some of the operators by the identity. Yeah, and then we say they're compatible if their like cones are disjoint. And this gives you an abstract polymer model partition function for mean values. So you could like reprove this result using like this language, and you could maybe get like tighter bounds, but I'm not sure. So this might give an alternative view of this result. So I think it's my final slide. So like, why should you care about this? Well, it has implications for like quantum supremacy and Hamiltonian simulation and machine learning, because it gives you like regimes in which case we don't expect quantum computers to outperform classical computers, or at least it gives you some idea of the type of systems that you'd need. It gives you a relationship between phase transitions and complexity transitions. So these, at least in the classical case, have been proven to be like at the same point. And the technique is like simple and versatile, so you can prove things quite quickly, and you can apply it to like a wide range of problems. So like the independence polynomial, you could do it like quantum circuits, Hamiltonians, like matching polynomials, Ising models, like anything you want. But like the different problems are, we'd like to identify an exact complexity transition point. So we'd like to know like exactly at which value of beta the problem goes from being like polynomial time to approximate to being sharply hard to approximate. We'd like to probe the transition point. So if you had like some experiment that like evolves some like system like this, we'd like to know how it behaves on one side of the transition and how it behaves on the other, or if there's like any observable that you could measure that would tell you what happens on either side. And we'd like to know like the relationship to other methods. And like what I'm working on now is trying to solve this problem now in the low temperature case. So like the high temperature case, we expect it to work because of these K correlations. And in the low temperature case, we expect like most things to be determined by their boundary conditions, which can help us. But I don't think this will work in general for the low temperature case due to like continuous symmetry breaking. But there are cases that are able to avoid this. So that's what we're working on at the moment. And I think that's all I have. So thanks very much for inviting me.
Clap, 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 clap. Thanks for the presentation, Ryan. That was really interesting. So does anyone have any questions I'd like to ask? Luke, you're going to take yourself off mute and ask a question.
That was just a clap, actually. But while I'm off mute anyway, so are you guaranteed, this may be an ill-formed question, but are you guaranteed that there's actually a sharp phase transition between the polynomial to the sharp p hard, or can you have some intermediate nonsense in between?
So I think that there will be, but I don't think it's guaranteed.
Yeah.
I was going to ask a similar question. Actually, and it's interesting because on the real line, there is a sharp transition, right?
Yeah, so we know there is on the real line for that particular model, but it could be like there are other models which don't have like a sharp transition, or it could like alternate between them.
Yeah, I mean, the intuition from the classical is that there's a sharp transition because for some magical reason there always is.
Yeah, you sort of like have like these dichotomy results where the problem's either in P or sharp P.
Yeah, it's either easy or impossible.
So I have a question. If not, I'll jump in before anyone else does. So do you have any intuitions to how the recent paper by Goldberg et al. Works around proving the sharp P hardness results for the whole plane?
Yeah, so they have this thing called like the Mobius program. So it's like very complicated. I don't really understand it, but they're sort of using this like Mobius recursion technique, which I think is similar to how Weitz's algorithm works, based on like decay of correlations. And they're using this to like interpolate to get to every other point. So in like earlier work, they have these like sets in the complex plane that like obey some like property, which means that you can like interpolate to other points. I don't understand much more than that.
Okay, cool.
I have a question.
Yeah.
Yeah, I was just wondering on this result you were talking about for a polynomial time approximation scheme for estimating the expectation value of products of local operators after a finite depth circuit.
Yeah.
Is there a promise that the gate library is sort of local or not too complicated, or is that?
You're just guaranteed they're close to the identity. So there's like this this condition here, which just says these local operators have to be like close to the identity.
Okay, but the quantum circuit, are the gates in the quantum circuit you can choose any library you want, or?
Yeah, it just has to be constant depth.
Okay. So they could be, like, it could be constant depth generated by a Hamiltonian which acts on all of the qubits.
Yeah, I think it has to be like local in some sense.
Oh, okay, that's the question I had. So it does.
Okay, yeah.
It does have to be local. Yeah. Okay. I see. So is it? So you're saying that your results give another way to see this result?
Yeah, so I've never actually tried it for like the mean values, but like I assume it just worked because their proof is like very similar. I tried it for the quantum circuits and that like definitely works. But I think like the main difference is that they use like the Lavash local lemma for like their proof of like radius convergence, whereas like maybe if you used like this Kotecký-Preiss convergence criterion, you might get something better.
Okay.
So, you have any more questions, Gavin?
Well, yeah, tons of questions, but actually, I think I should look at the paper. It was a good talk, but it's a lot to absorb.
Do you have any more questions? And if we don't, we might go to stop the recording, and then just go to a general chat if people prefer that. And that way, Gavin can ask all his questions. Okay, well, let's thank Ryan again for giving us a great talk. It's really interesting.
Thanks for inviting me. It's good to see you all again.